Hi. Now we are going to learn about some applications of second-order differential equations into economic problems. We're going to start with market model with price expectations. Look, generally we're going to use the model we've been using thus far in different contexts, but we are going to introduce price expectations into it. And we're going to assume that customers care not only about the current price, but about the price trend. How can we introduce price trend? Well, we can use first derivative. So, first derivative will tell us if the price on the market is increasing or decreasing. Of course, depending on the sign. If the sign of the derivative is positive, price is increasing, and if the derivative is negative, of course the price is decreasing. But let's just assume one more thing, that people care not only about the price trend, but also about whether the price are increasing faster and faster or slower and slower, whether they are decreasing faster and faster or they are decreasing slower and slower. We can introduce the expectations about the changes at the rate of growth of prices by the second derivative. So the second derivative is going to tell us if price is increasing or decreasing at an increasing or decreasing rate. Okay, so how do we gonna introduce those two into a model? In a very simple linear way. So the model we've been considering thus far, with different extensions of course, but in the most basic form is given by quantity demanded equals to alpha minus beta p, quantity supply equals to negative gamma plus delta p, and with equilibrium condition, quantity demanded equals to quantity supplied. Now, just as before, we are assuming that all parameters alpha, beta, gamma, and delta are all positive. But now we are going to introduce first and second derivative in order to account for expectations. So, in demand function, we're going to add m times p prime plus n times p p's. We are not going to assume right away the values of m and n, but let's just elaborate on their meaning on the example of parameter m. Look, if parameter m is positive, this means that if price is increasing, quantity demanded goes up. What does it mean? What does it imply for expectations? Look, if price is increasing and people buy more, it means people expect that the price trend will continue into the future and the price is going to increase even more. So consequently, here people buy more today in order to avoid even higher price in the future. And look, it also works in the opposite direction. If price is decreasing, this implies that quantity demanded goes down. So even though the price goes down, people buy less. Why? Because they expect that the price decrease will continue into the future. And it's better to wait with the purchases for the time when price is even lower. Now, on the other hand, if M is lower than 0, this implies that if price is increasing, quantity demanded goes down. Well, look, it follows from the law of demand. But here, we have another explanation for this. Look, in this case, people expect price reversal in the future. So now they purchase less because in the future they expect that the price will reach some limit and then it starts to fall, and this is going to be the perfect time to make their purchases. And of course it also works in the opposite direction. When price is going down, people purchase more, which again is intact with the law of demand. But here we see that if the people observe negative price trend, if they purchase now more because they expect reversal, that in some point of time price starts to go up, so it is better to purchase more right now. Okay, so a very similar very similar interpretation we could impose on parameter n, but this time it is associated whether the price is going to increase further and further, faster and faster, or slower and slower. But to that we will get back a little bit later once we solve the model. Okay, so we can condense model into a single equation by equalizing demand and supply, as we always do. So now we put all expressions with P on the left-hand side and all the expressions without P on the right-hand side, and let's also organize them in a way that is more familiar to us. So starting with the highest derivative, the most to the left. So we get that this is NPBs plus NP prime. If I'm going to put delta P on this hand side, it will be with minus, so I can take minus out, and I'm receiving this expression. Also, if I'm gonna put alpha on the other hand side of the equation, I will have it will be with minus. If I take minus out, I'm gonna obtain this expression. And look, it almost looked like the expression for second order differential equations we've been working with, but the only thing that is different is this n. We do not like to have any coefficient on the highest derivative, so we divide both sides by n. Look, and now this is second order differential equation in exactly the same form as we were doing before. Now instead of y, we have p, so y of prime p prime, y bis, p bis. So consequently, this means that this is our parameter a1, this is our parameter a2, and this as a constant term b. Okay, so let's solve, let's first find intertemporal equilibrium of the model, which in this case will also be the level at which it will be an equilibrium in economic sense, because quantity demanded and quantity supplied are exactly equal at this price level. Okay, so our P, our particular integral for P is of course given by B over A2. So look, I'm going to take this expression, okay, let's just do it in steps. And now I'm supposed to divide it by A2. So I'm taking the reciprocal of this expression and then multiply it. Now look, minuses cancel each other out, n's cancel each other out, and we get the intertemporal equilibrium as well as market equilibrium is given by the very familiar expression alpha plus gamma over beta plus delta. We know that this number is clearly positive based on the assumption. This is the result we were always getting. Now, once we have intertemporal equilibrium, we can start looking for the complementary function. And of course, because we have everything written down in terms of parameters, not numbers, we can have three possible cases. So, case one is the case of distinct roots. This will take place, of course, if a1 square is bigger than for a2. So in our case, if m over n square is bigger than negative 4 beta plus delta over n. Then we can have case 2. Case 2 is the case of repeated roots. This one takes place if mn square is exactly equal to negative 4 beta plus delta over n. And finally, case 3, so case of complex root, takes place if m over n square is smaller than negative 4 beta plus delta over n. And of course, in each of these cases, we will have different roots. So under case 1, we see that the roots are given by negative a over 2, negative a1 over 2. So this is negative m over n divided by 2, or simply divided by 2n. And then we will have plus, minus, and we will plus minus square root of m over n square minus 4a2, but we have minus up front already, so plus over here we will have just one repeated root, and this will be equal to negative a1 over 2. So we've got that this is negative m over 2n. And finally, in case number 3, again we will have 2 roots, and those are given by, first we will have, but of course we will have complex roots. The first, the real part of a complex root is given by negative m over 2n, and then we will have plus minus. We need to change the signs of everything inside the root and take a negative 1 out, so we get that this is 4 beta plus delta negative 4 beta plus delta over n. I'm sorry, here of course divided by 2, and minus m over n square divided by 2i. And now look, what we are interested in is whether the equilibrium level that we found is stable. And in order to achieve that, we need to consider some cases. So let's start with the case number 1. So what if n is bigger than 0? Look, if n is bigger than 0, we can rule out case number 3 and case number 2 right away. And look, why is that? Because look, if n is bigger than 0, it means that this expression is clearly negative. If it's negative, it cannot be bigger than m over n squared, which is clearly positive. What is more, if n is bigger than 0, this expression is negative, this expression is positive, they cannot be equal to one another. So if n is bigger than 0, case 1 is possible. On the other hand, case 2 and case 3 are impossible. Okay, so look, this actually limits our considerations by a lot. We just need to deal with the case number 1. And now let's think. What can we get in here? Look, first of all, we know that equilibrium will be dynamically stable if both roots are negative. So, how can we be certain of that? Well, first of all, if n is positive, the value of this expression will depend on m. But we don't need to get this much into details with this. Why? Because look, with positive n, both of these two expressions are positive. So this implies that expression that we see over here is clearly bigger than expression that we've got over here, right? Because this is like m over n, right, to the power of 2 plus something. So this expression is clearly bigger than this one. Now, if this expression is bigger than this one, this doesn't matter. What is the sign of this expression? Because look, we are adding and subtracting. So look, we can think about it in this way. If it happens to be that m over negative m over 2n is smaller than 0, this is good, but what do we see? If I add a number to it that is bigger than this number will be bigger than 0. Of course, if I subtract, the number will be smaller. But look, here we would have root number 1, here we would have root number 2, and we want both roots to be negative. This is impossible under this case. So look, if at least one of these roots will always be positive, this means that this case is dynamically unstable. So look, what economic implications does it have? This tells us that in a situation where customers expect that price is going to be increasing at an increasing rate, then market becomes dynamically unstable and the price starts growing indefinitely. On the other hand, if this is also the case with n bigger than 0, if customers would assume that price is going to be getting smaller and smaller, this makes also the market dynamically unstable and the price ever decreases until it goes to 0. So this is what we get. This is the first conclusion that we get. If customers expect that the price is going to be increasing at an increasing rate or decreasing at a decreasing rate, then we will have dynamic instability and basically the market collapses. Okay, so now let's consider the other possibility. Now, what happens if n is smaller than 0? Look, in this case, we have two possibilities. Let's consider first the possibility that m is also smaller than 0. Okay, so look, in these circumstances, all three cases are possible. Okay, so let's go to case number 1. Okay, look, in this scenario, so when m is smaller than 0, we can be clearly sure that when both m and n are smaller than 0, this expression over here is clearly negative, which is good, because this is like we are one step closer to dynamic stability. And now, what do we see over here? This expression is clearly positive, but this expression is clearly negative. So look, now we have the opposite situation. The sum of these two expressions, because one is positive, one is negative, must be smaller number. And this means that this number is definitely smaller than this one in absolute, in terms of absolute value. And look, so here we can make a similar graph. We can be sure that negative m over 2n is negative. And look, we clearly also know that this expression in absolute value is bigger than the expression on the right, which means that one root, the bigger root, R1, is still going to be negative. So we see that under case 1, we have dynamic stability. Now, what about case 2? Well, in case of case 2, everything is very easy, because this is negative, which means this positive, minus up front, it's negative, both roots are negative, dynamic stability. And then we move to the complex root case. But look, for the complex root case, the only thing that matters for us is h. H is the real part of the root, and this is the part that decides about the dynamic stability. And look, again, we clearly see that that the market, that this root is going, that the real part of the root is going to be negative. So under all three cases, when we have negative n and negative n, we have dynamic stability under case 1, 2, and 3. Okay, so before we go to economic interpretation of this, let's consider what would happen on the other side, on the other hand, if m would be bigger than 0. And look, what do we get in this circumstance? Let's start over here. If m is bigger than 0 and n is smaller than 0, this expression becomes positive. Under case number 3, we see we have dynamic instability. H, real part of the root, is the same as the root in the repeated root case. Again, this is positive. We have dynamic instability. And finally, we are moving over here. We know that this part is positive. We are adding to it positive number, and subtracting positive number. So again, at least one of these roots must be positive. So look, in here we have a situation that that equilibrium is dynamically unstable. So we have dynamic instability under case 1, 2, and 3. And look, what does this imply to us? Look, the only possible scenario in which equilibrium is stable is when people expect that price is going to reverse the trend. So if the price is going up, the price should go down again at some point in time. And if people expect that this increasing trend is not going to continue indefinitely. Look, this actually points to how important are market expectations about our expectations about the future price. Because if we expect for the price to continue to increase or continue to decrease, this makes the market unstable right away. Now, during the workshops with Valeria, you are going to do some numerical examples in that. And this is it about a market model with price expectations. Thank you.